the forced convection, natural convection phenomenon is due to the temperature difference between the surface and the fluid. When a hot body is kept in a still atmosphere, heat is transferred to the surrounding fluid by natural convection. The fluid layer in contact with the hot body gets heated and rises up due to the decrease in its density, and the cold surrounding fluid rushes in to take its place. The process is continuous and heat transfer takes place due to the relative motion of hot and cold particles. Consider a hot object exposed to cold air. The temperature of the outside of the object will drop and the temperature of adjacent air to the object will rise. Consequently, the object is surrounded with a thin layer of warmer air and heat will be transferred from this layer to the outer layers of air. The temperature of the adjacent air to the hot object is higher, thus its density is lower. As a result, the heated air rises. This movement is called the natural convection current. Since the fluid velocity associated with natural convection is relatively low, the heat transfer coefficient encountered is also low. The heat transfer coefficient can be obtained from Newton's law of cooling as shown, where H is the average surface heat transfer coefficient, Q is the heat transfer rate, A sub S is the area of heat transferring surface, T sub S is the average surface temperature, and T sub A is the ambient temperature in the duct. The complexities of the fluid flow make it very difficult to obtain simple analytic relations for natural convection. Thus, most of the relationships are based on experimental correlations. The relationship of the Nusselt, Grashof, and Prandtl numbers are essential for calculations on natural convection to air from vertical shapes and horizontal planes. Where B and N are constants depending on the shape and orientation of the heat transferring surface, L is a characteristic dimension of the surface, Cp is the specific heat of the fluid, G is the acceleration due to gravity, delta T is the surface temperature minus ambient temperature. These are the properties of fluid that are measured at the mean film temperature. K is the thermal conductivity, ρ is the density, mu is the dynamic viscosity, and beta is the coefficient of volumetric expansion. The table presented consists of values of B and N for different shapes and orientations at corresponding ranges of the value of Grashof number multiplied by the Prandtl number. To incorporate the effect of natural convection in laminar flow heat transfer, the natural convection factor for horizontal tubes at values of the Grashof number between 10 and 10,000 may be obtained using this equation.
To demonstrate the concept of natural convection, this is a problem taken from a cave. Air at 1 atmosphere pressure is passed through a horizontal 2 inches Schedule 4T steam-jacketed steel pipe at a velocity of 1.5 feet per second and an inlet temperature of 68 degrees Fahrenheit. The pipe wall temperature is 220 degrees Fahrenheit. If the outlet air temperature is to be 188 degrees Fahrenheit, how long must the heated section be? To solve the problem, we will be using Microsoft Excel. First, we break down what is given in the problem as shown. The numerical values are in a separate cell from their units, so it would be easier when solving throughout the problem. The average temperature is calculated first to get the values needed at that temperature. The diameter was taken from Appendix 3 and the viscosity from Appendix 8. The density is calculated using ideal gas from 68 degrees Fahrenheit. From that, we can solve the mass velocity using G equals V times ρ. Then, we can calculate the Reynolds number using GD over mu. We then obtain a laminar flow after we plug in the values. This verifies the equations that will be used in the process. First, quantities are needed such as specific heat from Appendix 14, thermal conductivity from Appendix 12, viscosity at the wall from Appendix 8, and cross-sectional area of the pipe from Appendix 3. Then the mass flow rate can now be calculated by multiplying the mass velocity and the cross-sectional area of the pipe. Heat load can be calculated using the formula mCp delta T. Then the log mean temperature difference is needed in the formula of the heat transfer coefficient and is calculated using the formula shown. From Appendix 3, we can get the area in terms of the length. Substituting the values from the formula of heat transfer coefficient, we obtain 6.82 over L. Another formula of the heat transfer coefficient used for laminar flow is shown. After substituting the values from the formula, we get 0.9813 over L raised to 1/3. Equating the two relationships of the heat transfer coefficient, we can obtain the length, which is 18.32 feet. The length obtained can be corrected for the effect of natural convection. This requires the calculation of the Grashof number. First, we can calculate beta at 128 degrees Fahrenheit. Delta T and density is also obtained. From the given formula of the Grashof number, we can plug in all the values we have and obtain the Grashof number. From this equation, which is the formula of the effect of natural convection, the value obtained here is used to correct the value of the length before by dividing it from the first length calculated. So the final value of length now is 13.6619 feet.